For section 1.4, at least the first part, we're looking at finding the rate of change. So practicing using slope, being able to calculate it between those 2 points. For number 2, I'll do number 2 and number 4. So for number 2, the first thing that I want to do is identify which one is my first point and which one is my second point. So my x2 and my y2, my x1 and my y1. And something to consider, and this is on your blue sheet, is we are looking at the rate of change of y, the rate of change of x. So the change in y and change of x. We can take the y values and subtract them, and the x values and subtract them. So we're finding the difference between the two. So we would just take and we would plug in those numbers based on what we see. The y2 was -3, the y1 is -37, the x2 is 4, and the x1 is 12. So here we would be looking at a negative times a negative being a positive. So -3 plus 37 gives me 34. 4 minus 12 gets me -8. I would love it if you reduced that down, simplified it. We recognize that we can divide both of those by 2, and so we would have -17 over 4 as your slope. For number 4, same process. x1, y1, x2, y2. We're finding the change in y over the change in x. We're taking the difference of our y coordinates and the difference of our x coordinates. So in this case, we have a y2 of -40 minus a y1 of -75, an x2 of -15, and an x1 of +55. So yet again, here we have a negative times a negative being a positive. So -40 plus 75 gives me +35. And -15 minus 55 gives me -70. And once again, if we can reduce that down, it would be really good. We want to reduce it down, and we actually, when you do this, you can divide it by 5, or you can actually divide it by 35, and you would get -1 over 2. For the set portion of today's assignment, it's really hard to do the evens here, so I'm just going to have to do this table for you. It helps a lot to go back and read what the situation is. Basically, Adam has some horses, and he's trying to figure out how to optimize the fencing for his horses. Each piece of fence is 10 feet. So 1 unit equals 10 feet, which is something that you're going to need here shortly. But for right now, we can just focus on the units of fencing. We know that we have a total of 16 units of fencing. So we're trying to figure out how much, what can our dimensions be? We know that one of them, one side is 1 unit, the other side is 7 units. Well, that means that if one side is 2, then we can say that the other side is 6. One is 3. So the other has to be 5. One is 4. The other has to be 4. Then if you notice that it's creating a pattern, makes things a little bit easier to see. Now, since we know that the length of each unit is 10 feet, we know that the length of 2 units is 20 feet. 3 units is 30 feet. 4 units is 40 feet, and so on. Whoop. There we go. And the width, same thing. Each one is going to be 10 feet. But in this case, the 7 units gives me 70 feet. So 6 units gives me 60. And hopefully you can see a pattern, again, starting to form. Now the perimeter, that's weird. It's all the same. Well, it's because it's the same amount of fence. We know that we have 16 units of fence. So if you were to take these pieces over here and you were to add up all of the pieces of fence, you would end up getting 16, or times 10 gives me 160. Okay? For example, just picking one out, 3 units and 5 units, we know one side of the pen will be 3, the other side will be 5, which means that the opposite sides are also going to be 3 and 5. If I add those together, I end up getting 16. The tricky part comes with the area. To find the area of a rectangle, we take the length times the width. So we will take, in this case, the length times the width. 20 times 60 is 1200. 30 times 50 is not 35, is 1500. 40 times 40 is 1600. And make sure you're including units on these. And 70 times 10 is 700. So again, we have a pattern that's starting to form here. 12, 15, 16, 15, 12, 7, back down again. So to discuss Adam's findings, explain how you'd arrange the sections of the portafence so that Adam will be able to do less work. We're trying to make it so that the horses can graze on the most amount of field as possible. Well, if that's the case, then what he should be trying to do is trying to optimize the fences that he's using. So what he should do is he should be able to create a 40 by 40 foot pen, and then I'll let you figure out what that looks like. Why would it be better to have a 40 by 40 pen than a 70 by 10 or a 60 by 20 or a 50 by 30? Now, to make a graph of that, what I would encourage you to do is to go into Desmos and be able to say that when the length is 10 feet, the area is 700. When the length is 20, the area is 1200. When the length is 30, the area is 1500, and so on. When you do this, you'll end up getting a graph that looks something like this. Now, this is just connecting the points, but what you can see is that we have an area of fencing that's growing, reaching its peak. Look at that, at 40, 1600. If you look back in the table, you should see, like, what is happening there and why is it happening? And as that was discussed in class, if we create the function, we should be able to have f of x equals x times 80 minus x, which means that we're going to take our length, subtract that from 80, and that will give us our width. Length times width gives me the area, and yet again, when the sides are 40 feet each, our area is 1600 square feet. So hopefully this helps. Again, I would encourage you to use Desmos as necessary to be able to refer back and just reference that. Just go back and check to make sure, is my work correct? Let me know if you have any questions.